Hello, how are y'all doing today? My name is Bernie Thompson, and today we're here to take a look at this little 2018 Honda Fit. This little Honda Fit is here from another shop, and apparently it's been bounced around from shop to shop trying to be diagnosed. The problem with this vehicle is it's setting a P0172. The system is too rich. It has a 1.5 GDI engine in it. So the first thing I want to do is get a scan tool and get some basic data so we can figure out how to diagnose this vehicle. So let's go ahead and get that scan tool connected. Okay guys, I got the scan tool, I've got the data coming up. We're rich and going from between rich and stoichiometric, and we have a total trim problem and a long-term trim problem. Both, and these are really bad because it's red. We have good engine vacuum. Let's go ahead and just raise the throttle and see what it does. Now we're just staying rich with a control problem. So we don't have enough trim to fix it. That's what that tells me. If I can't get into a stoichiometric condition and I'm rich, I don't have enough trim to fix the problem. So let's go ahead and take a look at the DTCs. So we have a DTC here, a P0172, system's too rich. So what we need to do now is we want to go to the sharpshooter and we want to go to the fuel trim tables, and I want to load these fuel trim tables. So we can go ahead and start this. Okay guys, let me warn you right now, you cannot diagnose a car like this if you're sitting in your bay. You need to run the fuel trims through the dynamic range. You've got to go drive these cars so you can see the trims dynamically, and that's going to help me understand how to diagnose this car. So let's go ahead and hop in and let's go for a test drive. Okay guys, we're out on our test drive, so let's go ahead and get the data. So the first thing I want to do is I want to load these cells. These are load cells. So what we're going to do is we're going to start to drive, and we want to just drive real easy, and you got to drive it through the dynamic range. So we need to fill out, we want to just drive it easy to wide open. Okay, this car has a real problem, guys. It's taken away a lot of trim. Okay, so let me pull over here where we can look at this data. Okay, so we're taking away a lot of fuel at the bottom and it got better. So let me show you how to do this. We're going to take it over here and we're going to plot that or graph it. So this is our fuel trim. We're taking away 45% down at light load, and as we open the throttle it got better and it went to about minus 20%. So it was taking away a lot of fuel down low, and as we rev the engine it got better. That's what that's telling you. So now is what we need to do is we need to run a volumetric efficiency test. Okay, what we're going to do is run a VE test. Go ahead and start this. It's a 1.5, it's about 60 degrees, so that's about right. I'm at a mile high, 5,500 feet, so we're good here. So all that data is good. So now to run the test, you want to just start to step into the throttle, roll in really quick. So we let it pull up. And we can see that these two traces, theoretical and the came up and they ran together. We can see how these all ran right together down low, and at the top the engine starts to pull more than the equation, just a little bit more. And you notice this is a generic equation. In other words, this isn't a scaled engine. And my guess is this little Honda probably pulls more air than my equation is doing. This is fine. What the difference is my trim is really bad all the way up through the middle, and it gets better at the top. So if we compare these, we can see that I'm good to the top. So the air isn't my problem. That's what this shows me. So let's run this test. So now we can see that this is my air, and it doesn't match the fuel trim at all. So this is my air, and this is my fuel, and I can see I'm taking away a lot of fuel down here, and I'm getting better. So what I want to do is we want to go over and we want to look at some data here. So the grams per second are 1.6, 1.5. There's a 1.5 engine, so I'm really close. Hot, unloaded, idle, I'm close. But I have a lot of trim. So let's go ahead and look at what that trim would be. Let's enable the PIDs. So what we're going to do is we're going to do this. So we're going to put total trim on the top, minus 46, and we're going to put the grams. So I got 1.5 engine, I'm reading 1.5 grams, so this is about what I would expect the air to pump right now, but I'm taking away 46% of the fuel. So this is a huge takeaway, but it's not air-based, so this problem is not part of the air. We have another problem, and the problem is on the fuel side. This is not an air side. So this isn't the mass airflow sensor, and I think they've already replaced that and a laugh sensor. I don't even know what all they've replaced. I have no idea. It doesn't even matter. The only thing that matters is we put the right part on. But this is not an air problem. That's what these tests right here tell me. Really heavy, and it's really important to look at the numbers right here, to look at where we're coming from, really heavy to better. Okay, so here's my air, we got good, and here we've got, basically, we're minus 45 moving to minus 20. So this isn't linear, it's not minus 40 to minus 40. My trim got better as I revved it. Now, if I had a problem where the injectors had a problem and they were the wrong injectors in the car, which I've seen from time to time, this trim would be linear. It would be 40 to 40, but it wouldn't be 40 to minus 20. Now, I could have gasoline in the oil, but I think I would have a better trim at the top. I'm still minus 20 once I've lost my vacuum even wide open. So I don't think that this is fuel in the oil, but we can test that when we get back to the shop really quick. But the air is basically reading correct. What's not reading correct is I've got a real fuel problem, and this has something to do with the fuel delivery. So we're going to have to figure that out. But by the way this trim is laying out, whenever I've seen injectors, it's always linear, and that's not linear. So I don't think that that can be the injectors. And I don't think that that's the fuel either. Now, the shop that this is at, he told me that this car came in on empty and he's put fuel in it. So he said it had the problem when he drove it over to the gas station, and when he filled it, it still had the problem. So the fuel has already been changed. So I'm not going to test the fuel because I don't think that's where my problem is. And I know it's not in the air right now. It's not an air side problem. This problem is in the fuel delivery side. So the first thing we need to do now is we need to get back over to the shop, and we need to make sure that the fuel is being read correctly by the RAF sensor and by the rear oxygen sensor. Okay guys, on the way back to the shop, I want to run one more test. I want to pick the rear O2, and I want to make positive that that rear O2 can go up and down, that it's not stuck low, because I've had one of these Hondas get stuck low and it was trimming to fix the cat, to try to fix the cat, and then the main trim was taking it back away. Okay, so we can see it's moving there. So the rear O2 can definitely make voltage, as we're seeing. So the rear O2 is not stuck low. I just wanted to double check that rear O2 because I have had a Honda have that problem. The first test I want to run to verify that the fuel is under control and we actually need that kind of trim is to use a gas analyzer. So we're going to take the gas analyzer and put it in the pipe. Okay guys, today we're going to use the 5-gas analyzer by Automotive Test Solutions, the Elite 5. This is an intelligent gas analyzer. It's pretty cool. It's a double-celled unit. There's 2 infrared cells. It uses a lithium ion. And what this gas analyzer is going to do is it's going to communicate to my scope over Bluetooth, so it's wireless. So I can have the scan tool data, the 5-gas data, and the scope data on one screen at one time. This is real innovation by Automotive Test Solutions. Okay guys, so now we need to acquire some gas data. So let's go ahead and start the gas analyzer. Now I'm going to bring up the multi-tool, and now I can pick anything I have selected. That's the scan tool Lambda. So now I've selected the scan tool Lambda. So this is Lambda from the scan tool, and this is Lambda from the tailpipe. Notice how those two match. That's the most important thing here. And I've got -46. Now we've got a pretty good burn. We've got 14.97% CO2 right here. That tells me I'm converting the gas well. I'm in fuel control. I have 14.62 air-fuel ratio and a lambda of 0.993. And I've got a lambda of 0.999 right here. This is what the RAF sensor, the LAF sensor is saying. This is what the gas analyzer is saying. These are the two that are the most important, because now guys, this is what we really need to do. We need to be able to see this kind of data. Now I want you guys to realize, what this means to us. That tells me in just a couple of second tests, I know that the entire computer and feedback circuit is working, because I can hit my lambda, I can hit my target air-fuel ratio, and I can keep the gases in control. And I can see this live while I'm taking away the 46%. I've got a lambda of about 1, and what's coming out the tailpipe is matching what the gas analyzer is saying. So this is just incredible. Right now, I know I don't have a problem with the feedback circuit. That's the oxygen sensor, the LAF sensor, and the computer. The actual computer has to take away the 46% to obtain a lambda of 1. So we now know that we don't have a problem in the feedback system. Okay guys, so now we know that under power braking or under power, it can still maintain fuel control. And we can clearly see that our trim dropped and the lambda stayed the same. So this feedback system is absolutely in control. I need to do one more test. Okay, so now what we want to do is hold the probe right over the oil fill, and what we're watching is the AC. Now if this is contaminated, we'll have several thousand parts per million. Anything over 700 parts per million, I have some contamination. But to have these kind of trim problems, we're going to see several thousand parts per million if it's contaminated. But when you're doing these kind of tests, anything over 700 parts per million on the AC, you have some type of contamination. So right away we can clearly see that we have no contamination. That's how quick and easy that test is, and it's accurate, guys. Okay guys, we've gathered this data. How do we use the data? That's what's important. What do we know? We know that we have a lambda of 1 and a lambda of 1. That means that it's not in the feedback system, and the computer is doing the proper calculation right here. Now without a gas analyzer, there's no way to determine this. But right now I know the computer is doing what it has to do to maintain a correct air-fuel ratio. We went out, we drove the car. We saw the trims aren't linear. They're going from 45, minus 45 to minus 20. Now that would tell me that I don't have fuel contamination, and it also tells me that the purge valve isn't leaking, because when I lose all the vacuum, I couldn't still be taking away 20%. So the fuel isn't contaminated and the purge isn't leaking. We know it's not on the air side. The mass air sensor is correct. So it's not on the air side. It's not in the fuel feedback system. When we have how much we take away is key to understand what's happening. So I think this is on the fuel pressure side. So now let's look at some fuel pressure data. Okay guys, since I think I have a fuel pressure problem, we need to check the fuel pressure reading. So what I came over and I got the high pressure fuel sensor right here, and I've picked English to read it in, and that will mean I'm reading it in HG, and that makes a real advantage for me. Okay guys, so the high pressure fuel pressure is right here now. Now that's 1025. Now that's in HG, so to make a conversion into PSI, I just divide it by 2.036, just divide it in half. So I've got 500 pounds of fuel pressure on that rail, and that's what I expect it to have. That's what I would think this engine should have. This is my lambda, so I've got a lambda of 1, and I'm taking away 46% right now, 47%. So the fuel pressure would appear to be good, and the lambda would appear to be good, and the trim is really bad. Okay guys, what I need to know now is what desired and actual fuel pressures are. So I got my Autel, and I can see that they're right on top of each other. They're the same. And it's about 500 pounds, and you know, this isn't an HG now, so it's a bigger conversion. I always like reading the stuff in HG when I can, because it's an easy conversion to get to PSI. Okay, so the way that this works is actual and desired are the same. Now when I was looking through my data, I was looking for data on the control. Is what I'm interested in is how much control there is on the high pressure regulator. If the sensor was misreading, and that's sort of what I think's wrong with this car, I think the data is telling me that the sensor's misreading. Well, you wouldn't get a code for that, guys, because the targets are all being obtained. But then I would have more fuel pressure in the rail, and I would overfuel it. And it would give me, as I rev the engine, it would have a change like I see. So I think the pressure sensor is misreading. But you're not going to see it like this, and there's no, I don't see any type of command for the regulator on this scanner. Okay, so that the pressure doesn't appear to be a problem right now. But what we got to do, I need to get a scope on this thing, and I need to look at the high pressure control and the sensor output. So let's go ahead and get a scope put on this and take a look at it, some more data. Okay guys, let me show you how I got my oscilloscope connected. I've got the oscilloscope ground connected to the battery ground. This is a high pressure regulator. I got channel 1 yellow and channel 2 red connected to the control circuit for the high pressure regulator. I've got channel 3 green connected to the current, so we can see a current clamp on channel 3 for the high pressure regulator. I've got channel 4 connected to the high pressure fuel sensor for the rail pressure. I've got channel 5 white and channel 6 purple connected to the number 2 fuel injector. And I've got channel 7 orange connected to the number 2 ignition coil. Okay, let's go get some data. Okay guys, I got the oscilloscope connected to this little Honda. Let me show you what I've got. Okay, channel 3 is an amp clamp on the high pressure control regulator. I picked 20 amps and I zeroed it. Channel 7 is an ECOP, so I picked 20 amps, which is a 10-time amplifier. I inverted it and zeroed it. Okay, let's go get some data, guys. Okay, I want to get my zoom window and I want to show you guys what's different about a Honda. Hondas do things a little bit different than some of the other OEs. Now the red is the control for the high pressure regulator. I want to turn it off real quick. The orange is the ignition pulse from the number 2 coil. So I want to take a cursor and I want to put it from the number 2 coil to the number 2 coil, and I want to mark it. Okay, so now look at the yellow is the control for the high pressure regulator. And notice how it fires every time I'm at top dead center. 1, 2, 3, 4, and I go back to where I started, 1. Okay, 1, 2, 3, 4. That would mean that this has got a 4-lobe cam. Now that's different because most cars that I look at have 2 and 3 lobe cams, but Honda does this a little bit different. They do a process to where I build pressure in the rail and then I open the injector and I leak the pressure off. I build pressure and I leak pressure. Let me show you what I'm talking about here. So this is my rail pressure right here. Now I want to clean that up. So I'm going to go to all off, I'm going to go to turn that on, and I'm going to smooth that data. Now I want to blow that up. Now what I want to show you is, do you see how I had a regulation event and I built pressure and then the injector turned on and I leaked the pressure off? Always remember, the injector is a leak. It's leaking the fuel off into the cylinder. I'm leaking the pressure out of the rail. I built pressure and then I had an injector and I leaked. I built pressure and I had an injector and I leaked. Notice how they're all pretty similar. So I'm going to bring a cursor down and I'm going to show you that each one of these drops is about the same. Now that's what I would expect right now, because we saw that through the gas analyzer we're actually delivering about the right amount of fuel. If one cylinder got a lot of fuel, like I had a bad injector, I'd have a misfire and I'd have a lot more hydrocarbon out the tailpipe, which I didn't have. What I have is pretty good burn, and I can see that each one of these drops. So right now, this looks like it's doing about the right thing to me. I built pressure and I dropped, built pressure and I dropped, and they're all equal. And that's about what I would expect. Let's go back out here. Okay, now there's something else right here. Do you see how this is top dead center and 30, 60 degrees after is my injector? See how my injector right here, the injector is turning on about 60 degrees after top dead center. That's where I expect this. As long as we're here, let's just take a look at something real quick. I want to just see how long that injector's on for. Okay, so I'm on for 909 microseconds, almost a millisecond. Now that seems awful long to me right off. But I want to look at, I'm going to come back to this. We came over to look at the regulator pressure, how it's being regulated. So that's what I want to do first. Okay, this is notice how the voltage went high and I got a ground. And this is very common on how Honda controls this. They get full voltage and full ground and I build current really quick. Then I start to pulse the voltage, and that's a current limiter. Now do you see how the current came up real quick, real fast, and then I limited it? Right when I start to pulse it, this green is my current from this, and you can see how it limits right when I start to pulse. Now I'm no expert on these Hondas, guys. I don't work on enough of them. But the other Hondas that I've seen, and they're turbocharged, so I don't know it would be the same, but this current limiting starts right after I get full voltage, and then I get current, and the current starts to limit way over here. This seems long. And anytime on these systems when I want more fuel pressure, I command more full current and I get more fuel pressure. So this seems like I'm commanding a lot of fuel pressure right here. It seems like that's going to command too much pressure. So if I'm commanding too much pressure, in other words, if this pressure right here in the rail at 1 volt, that should be 500 pounds, and at 1 volt I'm 600 or 700 pounds, and to get the 1 volt, if I'm out of calibration, I would have to command this on longer. Now I just don't know enough about Hondas to know, and I haven't looked into enough of these. I've only done turbocharged cars right now. But this seems wrong. It seems like I'm commanding too much on time. But guys, there was something I saw over here on the injector that I gotta go look at. We gotta look at this because there's something else wrong here. Let me show you. Okay, so right here is an injector. So let's look at this. Here's my injector. Okay, we have 950 microseconds. Now I expect this to be 700 to 900 microseconds. Remember, there's 500 pounds of rail pressure. We already looked at that. I want to get the calculator and I want to do something here. Okay, so we're going to go over and get the multi-tool. I'm taking away 44% trim, 44% trim. So I'm going to put 1.44 and I'm going to multiply it by 950, which is my on time. Okay, that's what the computer figured its base injection on time is. That's a lot of injector on time, guys. That's a millisecond, 0.3, 0.4 almost. That's like port injection on time. Now port injection, if I had that, I would think that would be about right at idle. But a port injection only has 40-50 pounds of rail pressure. This GDI has 500 pounds of rail pressure. This is way too much on time. So what that's telling me right now, guys, okay, my lambda is going off right here. Let's go over here. My pump automatically turned off, so let me turn the pump back on here. The pump automatically times out in 20 minutes. So now we'll get the lambda back on because the pump will start pumping it. And we'll see that the lambdas match, 1 and 1. I'm still taking away 44%. Okay, so that's my injector on time that's calculated by this PCM for on time. Now this is idling engine, guys. Now the main thing that would get me here would be the grams, gram weight. Now I'm only 1.3, 1.4 grams, and this is a 1.5. So the weight of air is entering in right. Now one of the other things that might get me right here is the baro. I'm 83 kPa because I'm a mile high, so the baro is right. The baro is right and the grams per, so the two basic air are correct. Now let's see if I've got air temperature selected. So let's go back over here real quick and let's look at, so the air temp 105, the engine's been running right, that's about right. So this would have to be like minus 40 before I could start getting any kind of real add for temperature. So the air temperature, the barometric pressure, they're all right. So the main parts of the equation that I can see right now seem like they're right. But this is way too much calculated on time. That's what the processor figured it was going to be by the base equation. Now is what happens is that's after I take away 44% trim. I'm pretty close to where I think it should be. 900 microseconds, 800 microseconds. But okay, at 900 microseconds, we have control because we got a lambda of 1 out the tailpipe and by this O2 sensor. But that's only after I'm taking away all that fuel. That's what the base equation is. So what I got to do now is I need another scan tool, and I don't know much about Honda. I don't know if they have alcohol calculations in these cars. But guys, I've been burned on this problem right here on a Ford. Because Ford calculates alcohol content, and if the alcohol content it calculates is too high, it'll have to trim it to fix it. I just don't know enough about these Hondas, guys. I'm no Honda expert. But I know where I've been burned on a lot of cars. So I'm going to go get a scan tool, an enhanced scan tool, and I just want to see if I have any alcohol contents on a Honda. Because that would be something that could get that base equation really high, would be if it thought there's a bunch of alcohol in the fuel. So let me go get that other scan tool and let's look through the data stream. Okay guys, I've got my tail up. I want to go through here. The engine speed is correct, and that's what the engine is reading, and that would be one of the base equation pieces. The map sensor, that just tells me I've got good vacuum. I'm a mile high and this really has good vacuum. The MAF sensor, 1.3, 1.4, 1.5, just like we've seen, that's correct. Baro sensor, 82, I'm at 83, so that's the right KPA. Now the battery would be something else I need to be worried about. 12.6 volts at the computer, and right now we don't got much charge, so this is what we have at the battery is 12.6. So if the battery voltage is really low at the computer, I don't know on a GDI engine, but on a port engine, that will increase the on time. So I want to look at that because that's something to think about. Okay, so here we got the fuel pressure from the PF, 1 volt, that's what we saw on the oscilloscope. 3,400 kPa, that's 500 pounds PSI. That's commanded, that's actual. So it's reading the command and actual. Now what I'm not sure of, if this sensor could be misreading, in other words, that's not 500 pounds at 1 volt. And it seems like I'm overdriving the duty cycle, and I don't see any duty cycle in this list either for driving the high pressure pump. But I'm not going to go down that rabbit hole right now, not when I can see that kind of injection on time. The injection on time on this at a millisecond or so is too much for a GDI engine at 500 pounds of pressure. So I don't think I want to go that way. So I don't see anything in any list that says anything about alcohol content. So this has something wrong with the PCM, so I need to check the powers and grounds, and something's going on with the PCM to cause this problem, because this is definitely a command problem. Yeah, we just commanding on too much injector on time, and then the trim is fixing it. But the base equation somehow is wrong in the PCM, or the PCM has a problem. But let's go ahead and go through this and check powers and grounds real quick to make sure that we got good current flow to the PCM. Okay guys, I brought a wiring diagram up on this little Honda. I found the powers and grounds. So first I've found all the powers. So the first thing we're going to check is the powers that go into this computer. So I'm in all the powers, and then channel 6, purple is on the battery, so if we had some type of a drop, we'll be able to see it more easily. And then I always like to have an amp clamp on the powers or grounds somewhere, so if something's pulling really high current and I pull all the current away from the computer and it can't operate the gates properly, I can see that very quickly. So it's always good when you got a computer style problem to have some type of an amp reading off of it. I've gotten burned on that in the past, and I've learned that I always put an amp clamp on when I'm checking powers and grounds somewhere, so I can make sure that there's not some huge current draw going somewhere that won't allow the gates in the computer to operate correctly. So that's where we're connected. Now let's go look at the powers, guys. Okay guys, I got the scope up. I've set channel 7 orange to an amp clamp, 20 amps, and I've zeroed it. So now let's check these. So basically we've got battery voltage on everything, and we got some current flowing right now. And the battery's not fully charged, but I've got battery voltage basically on it. And this is at the battery, so we don't got any big drop. The battery's just low. Okay, that's interesting. Wow, okay, that's really crazy right there. Okay, so the current, I'm pulsing something out of the current right there. So basically I'm pulling 13 amps of current, 13 amps of current, and it's very steady. So that's something controlled. That's some steady controlled pulse. Very different. And it's occurring at every 10 milliseconds of time. And we can see up here, and see the powers, and all the powers are dropping here. And I want to show you something. So if we measure our drop, on all the powers you're allowed a ½ volt. And I'm not going to start chasing stuff till I get more than ½ volt. So this is my drop during the pulse. And basically I've only got 221 millivolts of drop. So that's not even close to my ½ volt that I've got leeway on. Basically on powers, I've got about a ½ volt when I check powers, and I don't worry about too much. So my draw is right here. We can see that my draw is, 12, 13 amps of draw, but it's definitely steady. It's definitely at a steady pulse. And again, we can measure these ones over here that are different than what I just measured. And they come up at about the same, 9.7 milliseconds. So this is something that's being controlled, like something out of the computer. Now I'm not sure, maybe that's pulsing the tranny, or maybe that's because I have a computer problem, because we're looking at this computer because we have a problem. But the step 1 that I've got to start with, I'm checking powers and grounds for a drop that's big enough to cause me a problem. Now is what I want to do. Okay, so that's reverse right there. That's park. That's drive. Okay. Let's look at this. So we're definitely changing this pulse by changing the gear selection. Okay, we can see that the pulse has changed dramatically here. Okay, so I've still got about 10 milliseconds, but we're seeing that the control is being controlled differently now than when just the key is on. Okay, and the most important thing I need to check right now is what I came over here to check, is this voltage drops up here. Go to the bottom of the yellow right there, and then we'll go through the main body of the yellow. And basically I've got 279 millivolts. So that's not a ½ volt, that's only a quarter of a volt. So let's look at this. You see we're charging on all of them. right through the yellow there. And to the bottom of the yellow there, that looks like my biggest drop that I have. And again, 259 millivolts. Now at a quarter of a volt on the power, from all of my experience, I've chased a lot of problems like this and I never could find that's not a problem in my mind. I'm not chasing this, it's not enough. I can see that I've got a drop, but it's not enough to cause that computer to be having a problem in my mind. So right now I need to get on the grounds and I need to go through and check the grounds. Okay guys, I found the grounds in the wiring diagram. I found them on the connector. I've backprobed all the grounds at the computer. I'm on the negative battery cable with the negative scope cable, and channel 7 is still on the current out of the battery. The engine is running. Now the engine has to be running to see voltage drop. If the car won't run, you've got to crank the car over so you activate components to see voltage drop. Let's go ahead and check the data. This is the same thing we were looking at. It's the same app pump in the same place. We've already looked at that, so I'm going to shut that off for right now. Okay, so the only one I can see that's got some noise on it is the white one. So let's get the cursors. We're measuring from a spike to a spike, and that's 810 microseconds, or 1.2 K on the hertz. Okay, the only thing that I could think that's running at that kind of speed at repetitious is the throttle. So what I want to do is I want to go back and I want to look at this. So you can see this is auto scaling, so now it's bigger. It's no more worse, it just looks worse. Because I turned the orange off, so we're not scaling on the orange. So these are my grounds, and I can see that all the rest of my grounds are pretty good. None of them are more than a tenth of a volt. They're all less. Now I got bigger spikes on the white one, so I want to look at what the white one is. But again, I think the white for that frequency, I think that's the throttle. We're going to go ahead and stop this, or start this. That's what I want to do. So I want to go ahead and I'm going to show the engine. And then I'm going to open the throttle up. So I'm opening the throttle now. Off of it, I'm opening the throttle. So we can see right here when I open that throttle, I got way more spikes on here. Again, if we're going from spike to spike, 133 K on the hertz, 749 microseconds. So this is a really fast pulse. But again, we can see where it got bigger when I opened or activated the throttle. This is the throttle control, and that's a ground on the throttle control. Now, I don't think that that's more than I want to see. So I'm going to run a ground from that to the battery ground, and we're going to see what it does. But I don't think that's my problem either. Don't think that's what I'm looking for on this car. And over here we can see this. And again, over here we can't look at this. Why can't we look at it? Because there's no current flow. The engine's not running. The engine has to be running or cranking to be looking for a voltage drop. I can't emphasize how important this is. If you don't have current flowing, you cannot have a voltage drop. So let me get this running, get this started and running. And we can see right here, when it was off to when it came on, when we started it, we have a difference. And the difference is because now we have current flow, so we can have more of a drop. On the ground side, you basically want less than 1/10 of a volt. And you can also see the purple's moving more than I'd like to see maybe. Millivolts basically on that. This is a high point. We exceed our limit. So the purple's been moving more than I'd like to see it. And the white's moving. I think both of these have to do with the throttle. Because none of the rest of these quite have the same look. You can see where we got stuff turning on and off here, and that's normal when you look at ground for the scope. That's nothing to be alarmed about right now. I mean, this just aren't the big enough grounds that I could see to cause a problem like what we're having in my mind. Now, I want to go ahead and I want to connect the ground on the white wire. That's the throttle motor that's putting that noise out. So I want to see if I can't put a ground and we absorb some of it and see what will happen. What I have here is that is the connector at the computer, and I have a wire that I've run up right here, and I can plug and unplug it to the battery. So I'm running the ground directly to the battery so we can check the noise. Let's go ahead and do that. That's with it connected. That's disconnected now. You can see it got a little bit bigger. I'm going to go ahead and connect it. And we can see it gets a little bit better. Now guys, all of these motors on these throttles have some noise. Whenever you're looking at throttle circuits, you'll always see this noise because it's turning on and off the motor so rapidly, and that motor has some magnetic field and it's falling, and they're turning it on fast enough, turning it on and off fast enough to where the magnetic field can't completely fall, so it can hold that throttle plate very stable. This is more normal. This isn't what I'm looking for. This isn't the problem, guys. Don't get confused, because this is just a motor that's being controlled very rapidly, and you always have some noise off these motors. And apparently this ground has to do with that throttle circuit. I can already see it because I can open and close the throttle, and I can see it change the noise level. Once again, I'm going to unplug it. And we can see it gets a little bit bigger. And I'm going to plug it in. But I've checked lots of throttle circuits on vehicles, and they always have noise from that motor control system. The H bridge always puts noise out on the circuits around it. And the ground we're in must be the ground for that throttle control. And we can see that right away just because the frequency is so fast. There's not a whole lot of things on these motors that work with that kind of frequency other than a throttle control. Okay, now we're going to check the alternator for any kind of leaking diode that might affect that computer. Now the only way that you can check diodes is to be at the back of the alternator. And as you can see, I am on the output stud from the alternator at the alternator. Never ever go to the battery, because the battery acts as a huge capacitor and it can actually dampen these diodes where you can't see them at the battery. You always want to be at the alternator itself to do diode testing. And that's where we are. So let's get some data. So we're collecting the data here, and this is off the alternator. So let's go ahead and look at the data. We need to zoom in. Okay, now what we're looking for are these little humps here. This is the alternator winding putting out, that's the diode clipping it. This is the winding putting out, alternator clip. Winding putting out, alternator clip. And it's what I'm looking for usually is if I've got one diode leaking, every third one of these will have a big drop. And these drops here, like these drops, this is just from things turning on that are pulling energy and I'm changing. Don't get confused on that. What I want to look at is the hump and the cut. Hump, winding output, diode clip. Winding output, clip. Winding output, clip. And I'm looking for one of these to be dropping, and it will be repetitive. If it's leaking, it's going to be repetitive. And I also have the fan on high, so I'm loading this alternator. There's a load on it. So it's putting out current right now. And so we can see, and I can see that there's no diode leaking. So now, okay guys, we've checked the major powers and grounds. We've checked the alternator for a leaking diode. I'm trying to do quick, easy tests for things that might have a logic problem, where I could get a gate shift in the computer where I could be having a problem like I'm looking for. Okay, so now I want to do one more quick, easy test, and that's to drain all the capacitors out of the computer so the computer's totally drained. And then I want to start the car up and watch the injector on time to see what happens. That way we can see if when we drain all the capacitors, if I don't reshift the gates and the logic gate comes back and the computer starts to work properly. So it's a real easy thing to do. And then the next thing I'm going to have to do is I want to lift so I can get this car up in the air, and I can go through every single wire on this computer. All we've done is check the major powers and grounds. But what I'm going to need to do in the end is to check every wire that goes into and out of that computer, and all the inputs, like the vehicle speed sensor. When I get in that wire, I need the vehicle to be able to spin the tires to make sure I have voltage changes on those wires. Every single wire, when you're checking a computer, you got to check every wire. The engine has to be running so you can produce voltage drops, and then you have to make sure whatever voltage state of change should happen on that wire occurs correctly. Now, this is a very time-intensive process. It takes 3 hours plus to go through a computer wire by wire like that. So I don't want to do that right now, but I'm headed that direction. But before we get there, let's just see if we can reset these logic gates in this control unit. Okay, what I want to do is take the negative cable off the post of the battery. Pull that back over here. I have a 10 ohm resistor in this drain wire. And I want to just connect it across. Now is what I want to do is I want to let that sit for about 10 minutes. I want to drain the computers. Mainly is what I'm trying to do is reset the gates on the PCM here. So let's just let that sit and then let's see what we get. Okay guys, that's been 10 minutes. So I want to go ahead and put this back together. Now let me get the scope set up on the injector. Okay guys, I've got the fuel injector for number 2 up on the screen. I've got the scan tool lambda right here. I got the scan tool total trim right here. And I've got the scan tool fuel pressure here, and the RPM is right here. Now the car has not been started, so this is a fresh start. Go ahead and start it. Okay, so now let's go ahead and And we can already see that this is on for a long time, because you see how much time we have current limiting over here. We give full voltage and full ground, and then we go into a current limit here. Okay, so the injector on time is on for 2.32 milliseconds. Now for a cold start, that's not all that bad because the engine has not been run. It's still a lot of time, but that's if it was hot and I had that much like it did before where we had 1.4, that's just too much. Let's go ahead and get some more data. Now that it's run just a little bit, let's see what we get for. And we can already see it's coming down. See how I have fewer, that I'm coming down because I'm taking away 25% trim already. .7 milliseconds on time now. But what's really interesting is this car came up with 2.5 milliseconds of on time to get it started. It just seems like an awful lot, but a cold engine, a lot of GDIs cold get a lot of on time to get them started. I've seen that before, but I haven't seen where they're at 1.4, 1.5 with a hot idle. So it's very interesting. But this car, whatever it is, the gates didn't reset, but the base program, this almost seems like this is programmed into the car to me right now. Because that came up and it didn't have any time to be influenced by any outside force. Okay guys, I had the technician that I'm working with at this shop ask me two really important questions. And so since I have to answer him, I thought I would answer everyone because he's going to ask similar questions to a lot of you. The first question he asked me is when we saw those voltage drops on the powers, why am I not worried about those drops on the wire? Okay guys, let me explain this. On the power side, I'm looking for a logic problem. If I have 12 volts and it's basically 12 volts going into the computer, that feed is going to be processed and it's going to have big capacitors on it to help steady that voltage out in the computer. And the other thing that I've got is once I store that voltage in the capacitors, now I'm going to regulate that down because any of the logic that a processor is going to use is going to be at 5 volts or 3.3 volts. So if I've got basically 12 volts and I have a steady stream into a capacitor, I've got more than enough voltage where I don't got to worry about it because I know I can process that down to 5 volts or 3.3, and we're dealing with a logic gate problem here. So can I keep the logic alive? Well, if I've got a steady 5 volts or 3.3 volts to the micros, the answer is yes. So no, I'm not worried about the voltage and the noise I saw on the power because that's all going to be taken care of through capacitors and regulation circuits. But he asked me a second question that I really had to stop and think about. He says, what's wrong with that kind of on time? What's wrong with 1.5 milliseconds of on time? Okay, now that got me thinking now. Okay guys, let me explain something. At idle, I have 150 milliseconds for a fire cycle. That means that I have about 37 milliseconds, we'll call it 40 milliseconds per stroke of on time. Now with port injection, I can tie 4 strokes almost together, and all I got to make sure that I don't go past the on time of the injector, whatever my maximum RPM is. The higher the RPM is, the bigger the flow the injector has to have because I'm going to have enough fuel get into the cylinder to have a combustible mixture. And I'm going to have to beat the time of my stroke limits. So at idle, I have 40 milliseconds, but at 6,000 RPM, I only have 20 milliseconds for a fire cycle or 5 milliseconds a stroke. So if I put all strokes together, I have 20 milliseconds. Now if I have 20 milliseconds, that means that my injector on time can't go past 20 milliseconds or I lose control. I've got to be able to shut the injector off, let the injector reset, and let the gates reset, and I need about a 20% margin to make that happen and be accurate. That's why we see in port injected cars, my maximum injection on time on a lot of cars is going to be 17, 18 milliseconds. If I get towards 20 milliseconds and I only got 20 milliseconds, I'm going to run out of control. Now on a GDI car, this all is going to change. Now, when I've got to give full fuel to this engine at 6,000 RPM, I've got 5 milliseconds to give my injector on time. So at idle, I've got a lot more time because I got 20 milliseconds of stroke, but at 5,000, 6,000 RPM, I'm going to have 5 milliseconds. So why would an engineer have, more than a millisecond of injection on time when I won't need it? I got to make sure that the injector flows enough to where I can control my idle, but when I open the injector up for only about 5 milliseconds of time under full load, that I still have enough time to get the fuel in. Now, GDIs play games with this. That's why I changed my fuel pressure with the high pressure pump. So I can go up to maybe 2,700 pounds I've seen on some cars, but a lot of cars run under load, 22, 2,500 pounds of pressure under load. Okay, so if I'm already on for 1.5 milliseconds at idle, I don't have a lot of change to be under 5 milliseconds to get my injection on time during my induction stroke on a GDI engine. So that's why we see short times generally at idle. Now what does Honda do? Could this car actually be programmed right? It might be able to be. I'm no Honda expert. It just seems like 1.4, 1.5 milliseconds of on time is too much on a hot idle, a hot, good running idle. It seems like it should be to me like 900 microseconds. Under a millisecond is more what I would expect. But do I know that 1.4 or 1.5 is not right? No, I don't. So this was a great question he asked me because I got to start thinking about my theory I'm using on this car. So I know now I'm going to go find another one of these cars and I want to see what the injection on time hot unloaded idle is going to be. Is it going to be 1.4, 1.5? It just seems like a whole lot of time when I'm dealing with the physics of GDI. So I'm going to go find another car and we're going to see what that car does. Okay guys, I went out and I found another Honda Fit. No, it's not an 18. The only other Honda Fit I could find is a 16. But it has the same basic system in it. Now what I saw on that car is it has a higher gram weight going into the engine at idle. It had 1.7 grams at idle and the injection on time was 1.7. Like even longer than this car. So that tells me that that's what they want, that this car is programmed to have a long injection on time at idle. And they're going to make up for it between the on time and the fuel pressure. So now that we know that the injection on time is correct and the minus, the fuel trim is being taken away from the base equation is correct. So now what I want to do is we're out on a test drive, so let's look at some data. Okay guys, so this is my number 2 injector. This is my Lambda and we're a little rich right now and I'm taking away 47% trim. The fuel pressure is, divide that by 2, so I got about 500 pounds and we got an idle at 620, 30 RPM. Now one thing I want to do to start with real quick is we haven't checked one of these injectors with it just sitting here and I'm in gear. When we were at the shop, all the testing was in neutral. Now we've got a light load on it, so let's do apples to apples. Okay, so I got 121.21 milliseconds, and I've got 500 pounds of rail pressure, and that's right now at idle. That's what I got. Now is what I want to do, is I want to go ahead and I want to accelerate the car, and we want to get the trim to fall a little bit like what we had when we were out test driving. Okay, I'm in the 20s right there. Okay, so what I want to do is I want to go ahead and check this where we see this. Here's one of the injectors, and we can see how we have a lot of current limiting, which means it's on for longer. Let's see how much longer it went on for. Okay, 3.26 milliseconds, so it didn't go up that much. Now let's see what happened to our pressure. So here I'm recording the pressure over here. So let's move this to measure and zoom in on this. Now the green is our pressure here. Let's get a cursor. So basically we have about 2300 kPa, so we divide that in half. So basically we've got maybe 1200 psi. So we didn't increase the psi that much because we went from 500 to maybe 1200. And then our on time isn't that much more either because we're only at 3.26. Let's go get another one. Let's measure another one of these just to see what we get. Very interesting the way their control system is on this Honda. It's very interesting to see how things are controlled. Everybody's got to do something a little different. So here we got 3.38 milliseconds. Now, so we increased this, but basically we've maybe doubled it, and we haven't gone up a lot on the pressure either. Because the pressure's over here, and we're about 23.37 kPa. Divide that in half, and that's less than 1,200 pounds. So we got our maximum pressure and we've got our on time. Now we go from a really high idle time to not that high under a medium load condition. I wasn't wide open. I was just trying to get the trim to drop. So the trim dropped back into the 20s, and we can see that what we saw the other day when that happened, that the trim was dropping into the 20s from the 40s to the 20s, and now we see what's happening with the injector. It's very interesting, the control strategy. Now guys, what that's telling me now is something very, very different, very interesting, because now I can see from this control that I could have a non-linear trim from the way that this vehicle's being controlled through the injector. So I've got a lot of on time at idle, and it doesn't go up that much. So I could actually have the trim values that we're seeing where we go from 40% to 20%, and it would be non-linear. And the way that the control system is done with the pressure on this GDI could definitely, if these injectors are the wrong injectors, I could be having this problem. Very interesting problem, guys. Let's go back over to the shop. Okay, guys, we're back over at the shop now. Now that I understand the strategy and how they implement these GDI injectors, I can fully understand how I can have a stepwise change in my trim from taking away 45% to taking away 20%. I think the problem is in the fuel delivery side. Like I said in the very beginning, what I didn't think is I said that the injectors couldn't be because they're linear. But now I understand how they control these injectors. I could have a stepwise change. So we're going to get the shop to pull those injectors and check them. Okay guys, we're back over at the shop. And the shop pulled the injectors out and checked them, and the injectors were absolutely the wrong injectors. As the shop says, they're rice rocket injectors. He got the right injectors, and he's got the correct injectors back in this little Honda Fit now, and he's driven it quite a bit, and he's sure the car is fixed. So hop in, let's go for a ride, and let's see what this car does. Okay guys, the first thing I want to show you is I have no DTCs, and you can see right here all the monitors have been completed. The shop's driven this car quite a bit. So the next thing I want to do is I want to run the fuel trim load cells. Now you got to run this through its paces. So we need to run through all the load through its dynamic range. And we can already see, wow, look at the difference that that's made. So let's just go over here. Let me pull over where I can look at that data. It's not safe to be looking at data while you're driving a car. Okay. So -1 to -4, rather than -47 to -20. Look at that chart, guys. Okay, this vehicle is fixed. That's fine. Okay, I want to run another test, so let's run one more test here. Okay, guys, I want to run some scope tests, but right now I've got total trim over here. The fuel pressure is right behind it, so we got about 500 pounds. And the gram weight is 1.5, 1.6 at the mass sensor. And my RPM's down here. So let's go ahead and get some data. This is the injector, same injector, number 2 injector. So now is what I want to do is we want to, okay, first, let's just take a look at one of these just to see where we are now. Okay, so we have 1.8 milliseconds, so we're on for quite a while. This is more like the 16 I looked at that was 1.7, 1.8. Now we're there on our time, and we're not taking away a lot of trim. So now is what I want to do is I want to put this thing under a light load like we did the other day. Okay, so that's just a real moderate load. That's not wide open or anything, but that's just a good load on it. Pulling the weight of the car up, get our zoom window. Let's see what we got here. We can see right away it's on longer because you can see how much .35 milliseconds. Okay, that's really reasonable for a light load especially. And what you can see right here is the current limiting. Okay guys, that's it. This car is fixed. It's ready to give back to the customer. So let's go back to the shop so we can get this thing ready to give back. Okay guys, we're over here at the shop. This little Honda is ready to return to the customer. As we can see, it's totally fixed, runs fine. Okay, what I want you guys to take away from this is really data-driven diagnostics. This is what I'm trying to show you how to do this stuff. You know, you keep using the data, and if the data changes, you got to change the direction you're going. Don't get stuck in a rut, because you'll get stuck in that rut and then you'll crash. Follow the data. If the data changes, you got to change your diagnostic direction with the data. And my diagnostic direction changed several times with this vehicle. I'm not real familiar with these cars. I'm surely no expert on Honda. I'm no expert on any car, guys. I just know how to fix stuff. But I'm no expert on any of these cars that I'm working on. And sometimes you got to use your overall experience. The thing I really learned on this car is you got to be really careful now on how I've had lots of vehicles that have had the wrong injectors put into them. But they're all port injectors, which means I get a linear curve. This is my first GDI car where they've put the wrong injectors in. And let me warn you guys, when you start putting in the wrong injectors on a GDI, like whoever did this car, you can melt pistons, because this isn't just fuel going into the port. This is something to where you can create a lot of problems for the motor and you can damage the engine. So these cars aren't something we're going to just wing and throw a crazy injector in to see if we can get more power. That's insane. You know, and sometimes the hardest cars are where some insane individual has decided he's going to hot rod his little Honda. Like, wow, really? Okay guys, if you stay on track and you use data-driven diagnostics, you too will have good troubleshooting in your shop.